Time for us to do more practice with applications which involve finding volumes by looking at cross-sections. As always, focus on the setup. In applications, the setup is the most important thing. And the way that you get good at setting things up is through practice. So as much as possible, do these problems on your own. And if you're following along with the videos, make frequent use of the pause button and say, let me think if I can set this one up. Pause it and try it out. And then once you're done, let's compare answers. I think that you're going to discover that pretty quickly you're going to be catching up, and not soon after, you're going to be ahead, because I believe in you. You're great and you're wonderful. And I look forward to all the wonderful things you're going to do. But for now, let's begin. So our first problem. Find the volume of the shape which lies over the region x squared less than or equal to y less than or equal to 1 with a cross-section perpendicular to the plane at a fixed y value being a square with one edge lying in the region in the plane. Okay, so I think the hard part about this one is parsing. We have to sort of be like, what? Okay, so let's go through and try to get an idea of what's going on here. So we know we're lying over a region x squared less than or equal to y less than or equal to 1. So let's start there. So what do we have? We're in the plane. So x squared less than or equal to y less than or equal to 1 says what? Well, if we draw the two curves, and the two curves being y equals x squared and y equals 1, what will we see? Well, here's y equals 1, and here's y equals x squared. All right, so there we go. There's our two curves, y equals 1 and y equals x squared, and we know we're above this region. So this is our region that we're going to work with. Now what's happening here is we really have a shape that's sitting on top of this region. Okay, so now the next thing for us is to understand, what does this shape look like? And we're going to describe the shape by saying, look at cross sections. So let's think about what's happening here. A cross section which is perpendicular to the plane, so we're somehow perpendicular here. There's lots of ways to be perpendicular, at a fixed y. Okay, so that says, here's the idea, is when we slice this way, so in other words, we're just like coming in and out, all right? That's the way we're slicing. That's what our cross sections are, squares. So in particular here, if I were able to go up into the third dimension, lo and behold, I would see that there's a square there. And you know, there's down here, there's a little teeny tiny square sticking up. And of course, at the top, there's a big square, and so forth and so on. All right, good. We are starting to understand our idea. All right, so our cross section is a square. Now, good news for us, squares are easy to find areas of. So that's going to give us a good chance for us to make progress. All right, so what do we need to do? Well, we say, well, let's start with our formula. What's our basic formula for finding our volume? Now, the most generic formula of all for finding volume is the one that says that volume is you add up, which is what integration means. Integration is adding things up from wherever you start to wherever you stop. And what you do is you take the area of a cross-section times the thickness of your cross-section. And so we need to sort of get a handle, what's area and what's thickness. Now for thickness, we start to think about how we're slicing. And we use the problem to guide us. And it says we want to slice where we fix y, because that's how the cross-sections are being described to us. So we say, all right, so if we want to slice where we're fixing y, we really should be thinking of our small change. Our little thickness is in this respect. Our thickness is in the y direction, up and down. So this thickness will be dy. Now that we understand how we're slicing, we can also talk about start and stop. So how do we do that? Well, let's think about what's happening here. When we're slicing, what's the lowest value for y? the smallest y can get. Look at the picture. Here's our region. Where do we bottom out? Right down there, the origin. So we start at y equals 0. All right. Now, where do we start? In other words, what's the largest value for y? Where do we end? So as we slice up to there. What's the y value? It's 1. All right. Good. We're making great progress. To be fair, these are the easier parts to make progress on. But progress is progress. And it's always good to sort of like celebrate us moving forward. So now we turn to the area part. Well, we know it's a square, so it's going to be something squared. So what we have to do is think about, well, what's the something? So let's maybe redraw our picture because it got a little bit crowded there in the meantime. So what do we have? We have our parabola. We have y equals 1. And now our length of a side will be, if I can figure out what's that length. So here, this is one side of r squared. So I need to figure out, as a function of y, because I'm integrating with respect to y, what is the length of that side? Now, what that means is I really need to ask for the right minus left. I'm looking for the distance between these two parts. So how do we do that? Well, we say, look, we were given the functions in the wrong way. We were given as y equals x squared. That's not the way we should think about it. Instead, we should say, look, I really need to understand what's happening where x as a function of y. So we're going to do a quick change. So if we start with y equals x squared, well, I would take the square root. So if y equals x squared, what is x? Okay, be careful. What is x? There's two possibilities. So the two possibilities are plus the square root of y and minus the square root of y. All right, so that's what's happening with x. So it's going between positive root y and negative root y. So what's the length of the side? Well, you'd say, how far apart is it from positive square root of y to negative square root of y? Well, the way you compute it is you take the difference, square root of y, subtract negative square root of y, or 2 square root y. So for any particular height, the length of that side of the square is 2 root y. Now, we're going to take that and we say, all right, how do we use it? Well, that's going to go into the area as 2 root y squared. Because remember, we're looking for area, so you take the length times the length. So we now have all our pieces in place. Let's just clean it up, and hopefully what we have is pretty good. So we get, this is equal to integral 0 to 1. When we square that, 4y dy. Oh, beautiful. This is a great integral. The kind of integral we'd like to take home and meet our family because it's one that we can do. See, the hard part about this problem is not going to be the integration, which we're going to do in just a second. It's sort of like, initially we look at it like, there's a lot to process here. Well, how do we begin? But it's just sort of be patient, be methodical, think about what's going on. Think of the descriptions, think of the picture. What are we looking for? We're looking for a length. Okay, how do we find that length? What's the variable we're integrating with respect to? Well, how are we slicing? How does that guide us? Okay, so let's finish it up. The integral of 4y, well, would be 2y squared. Evaluate 0 to 1. The 2, because it's 4 halves. And plug it in. 2 times 1 squared, 2. 2 times 0 squared, 0. That part goes away. So our final answer, 2. Nice, nice. What a great problem. What a great problem. What a strange shape. I don't know. It's times like this I wish I was better at 3D printing. Well, someday, right? We should all have goals. We should all have aspirational goals. Mine is get better at 3D printing. All right. Well, of course, to get better at solving problems with volume, we do more problems. So let's do another problem. So, find the volume of the shape lying over the region x squared less than or equal to y less than or equal to 1, where the cross sections perpendicular to the x-axis are equilateral triangles with one side on the plane. All right. Well, what's changed here? Because there are some changes, and it's important to take a look. So let's come back, because a lot of this feels very similar to the other problem here, right? You see x squared less than or equal to y less than or equal to 1. Same basic shape. But what do we have? Here you have squares, and now we have triangles. Anything else? Well, sure. Look, here it's a fixed y, right? So that means we're slicing this way. Now, cross-section is perpendicular to the x-axis. Well, what does that mean? That means we're slicing in a different way. So there's sort of two things that are different. So, unfortunately, we can't just copy the answer from the previous one. We have to think about how we slice now. That's changed. And we have to think about our shape. That's also changed. Okay, but at least the beginning is very similar. So here we go. So we'll speed up through drawing the picture. What do we have? Y equals 1, y equals x squared. We can do those. Those aren't so bad. All right, here's y equals 1, y equals x squared, and we have our shape. Now, what comes next? Well, we should probably remember, since we're doing our problem about finding volume, write down our generic formula. It's always good to write down the formula. Even though we're like, wow, we've done it so many times, shouldn't we have it memorized by now? It's still good to write it down, just so we don't forget anything. So our volume is going to be adding up, start to stop, the area of our slice times the thickness of our slice. All right, there we go. There's our formula. And now we're going to dig into it and start to understand. So, first off, let's talk about equilateral triangles. That's probably a very useful thing to do. So, equilateral triangles just means that all the angles are the same and all the sides have the same length. So let's come over and do some computation. So suppose I have a triangle which is equilateral, and let's suppose this bottom side is L. So there's L. Well, what it means is that all the sides have length L as well. Equal sides, equal lengths. That's equilateral. Now, what do we need for the area? Well, you need the base, but you also need the height. And the way we get the height is, let's imagine dropping straight down. And if we did that, what we would see is it would cut the bottom in half. So that bottom half originally has length L. Now there's half L and half L. And that's a nice thing because of the shape. It's exactly cut in half. So, well, how does that help us? Well, it helps us in the last piece. It says, hey, these are now right triangles. I have the base, if you like. I have the hypotenuse. And now this missing side. Well, I have 1/2 L quantity squared plus whatever that missing side quantity squared has to be L quantity squared. A squared plus B squared equals C squared. Well, I can move this across. That really is a fourth. L squared, subtract L squared, says what I'm looking for, squared, is 3/4 times L squared, or my height would be, taking the square root, square root of 3 over 2L. So that's my height. What's my base? All the way across is L. So 1/2 base height. says the following. The area of that slice, the area would be 1/4 square root of 3L squared. It's kind of like a square. You know, you have that square. There's just this extra term in front, which gets us to the right shape. Okay, so that's going to be important. Now, let's think about what's happening. We're slicing perpendicular to the x-axis. So in other words, now our slices look like this. So if I slice here, oh, that's a little triangle. If I slice over there, a small one, there'd be a big one, so forth and so on. All right, so we need to start thinking about some various things. What's our thickness? Well, that's how we're going to slice. That'll tell us. We're slicing perpendicular to the x-axis. You know, perpendicular to the x-axis means we're slicing this way, which means that really, as I come along, what's my thing I'm perturbing? What's my thing changing? Is the x. So the thickness is going to be my change in x, my dx. Now, where do I start and stop? Well, I need to know what are my x values for these pieces. Well, when does 1 equal x squared? That's not so hard. We could do that. That's at +1 and -1. So that's our start and our stop. Our start, our low value, -1. Our stop is our high value, +1. Now, the area. You've got to think about this one. So how do you find the area? Well, the area, it says it right here. It's 1/4 times √3 times the length squared. So this area will be 1/4 times √3 times something squared. Now the question is, what's that something? All right. Well, to figure out what that something should be, we have to say it's this length, right, between the two curves. So L is here. So I'm going from the curve x squared to the curve 1, going back and forth. So how do we find L? What's the rule? Should we take 1, subtract x squared, or should we take x squared, subtract 1? Well, we're thinking of it as a measurement. It should be a positive. So we're going to take the one that makes it positive. To do that, we're going to use high subtract low. So that would give us 1 minus x squared. High value, top is 1. Low value, bottom is x squared. So now we're in pretty good shape. We're going to use one other thing. Let's look at our problem. Notice it has symmetry. And what we mean by that is if you look for the positive x part versus the negative x part, in other words, you were to chop it exactly in half, the two sides are exactly the same. Well, that tells us that we only have to compute half of it, then double to get the answer. Now, the reason I'm doing that is not because, any mysticism, but just because I really like 0. 0 is so nice, and I know you're probably like, 0 sounds so bad. If you have 0, you have nothing. Exactly. Nothing means no work, right? That's something to embrace and to celebrate. So yeah, 0 can be good. 0 can be a friend. So here we go. I'm going to, instead of going from -1 to +1, I'm going to go from 0 up to 1. Then I'm going to double. So there's a factor of 2. At the same time, I have the constant here, which I'm going to pull out. So I'm going to pull this out, times by 2, leaves us with a square root of 3 over 2. So just double that. So, okay. Now it's going to be 1 minus x squared, and then times dx. So let's go ahead and expand. So 1 minus 2x squared plus x to the 4th. There we go. So again, if you're trying to figure out where things came from, this 1 minus x squared is where that part came from right there. And then the 1/4 root 3 is where we got the root 3 over 2. And then remember we have symmetry, so we double. All right, now we're ready to integrate. This is a beautiful thing to integrate. It makes us happy because it's a polynomial. Polynomials are our friend. We love polynomials. And we're going to talk a lot more about polynomials as we get towards the end of the class. So, integral of 1, x, 2x squared, 2 thirds, x cubed, and then x to the fourth is x to the fifth over 5. Evaluate 0 to 1. See, here's where the 0 comes in handy. Poof, goes away. Nice. All right, we got to do the 1, right? Okay, so this is root 3 over 2, 1, subtract 2 thirds, add 1/5. Well, let's clean it up. So common denominator, this 1 is really a 1 over 1, so it would be, common denominator would be 15. So root 3 over 2, and you get 15 fifteenths minus 10 fifteenths, because you got to multiply by 5, plus 3 fifteenths. Okay, so let's see, what would that be? If I take 15, subtract 10 would be 5. If I then add 3, that would give me 8. So that's 8 fifteenths. So that part up here, that's giving me 8. But remember, there's a 2 downstairs. So that's very convenient. 2 goes into 8. So that will leave us with 4 fifteenths root 3. And there we go. Aha! Progress. Progress. Good. Nice. Fun problem. Fun problem. Well, of course, there are always fun problems whenever we're doing math. It's got to be fun. If we're not having fun, we're probably not doing it right. Okay, on to our next problem. So, you're constructing a solid where x goes between 0 and pi, and you draw the curve z equals tangent 1/4 x on the wall. And along the floor, you draw the curve z equals secant 1/4 x. Okay. Now, for each x, you construct a right triangle, where the height goes to the curve on the wall, and the base goes to the curve on the floor. Given that all units are measured in meters, determine the total volume of the solid. All right. Whew. There's a lot for us to figure out here. So there's a rough sketch here to help guide our picture. And I think if we add some labels, we're going to be in good shape. So what are the labels? Well, along here, this is our x direction. So this is where the floor and the wall are joined together. And this is the start. So this is at x equals 0. And back here, this is at x equals pi. Just pi. Yep, just pi, sorry. All right, so 0 up to pi. Now, what do we have? Well, along the wall, what we have is this curve up here. This is our tangent of 1/4 x. And then, along the floor, what we have is we have our secant of 1/4 x. All right, and then, of course, at every stage, we have a triangle. Now, here's sort of the interesting thing about this problem. The shapes are not the same. They change or morph over time. See, oftentimes when you have a problem like this, you're like, well, they're always squares, or they're always equilateral triangles, or they're always this, or they're always that. And here it's like, well, it's right now, it's a very long triangle, almost no height. Over here, it's a different triangle. It's not just a scaled up version. Things have modified. So now we're like, well, how do we do this? Well, the answer is we just say, look, let's run through the formula. The formula will guide us to make sure we get the right answer. So let's start by writing down our generic formula. So our volume is equal to adding up which means really integrate, start up to stop, our area of our cross-section, and the thickness of our cross-section. That's our basic formula, the place we should always begin. Start at the beginning. Now, we got to figure out what the pieces are. Okay, so let's think about, first off, what's the logical way to slice? The logical way for us to slice is we're really talking about how for each x we construct a triangle as we look at this cross section, which means that we should be slicing with regard to x. So that means our thickness, our perturbation, is going to be in terms of x. So that's what we'll have here for our thickness, dx. Where do we start? Well, we start and stop where x starts and stops, and it tells us x goes from 0, so that's the start, up to pi. And there's the end. Good. Now, what's the area? Well, now we say, look, our cross sections are always triangles. In fact, they're right triangles. They're not just any kind of triangles. They're the right kind. So the way we find the area, well, that would be 1/2 base height. So we can say, well, look, the base is going out to the secant. So 1/2 secant of 1/4 x. And then the height is going up to tangent. So tangent 1/4 x. So there we go. It's all there. So let's rewrite it and see what we really have here. So the half, we can pull that in front. That's a constant, 1/2 integral 0 to pi. Then we have secant 1/4 x and tangent 1/4 x. And now we say to ourselves, aha, secant times tangent, beautiful. Mwah! This is one of our 10 favorite things to integrate because it's on our list of 10 things we should know how to integrate. It's a beautiful, beautiful integral. In fact, secant tangent is one that we have memorized in our hearts. Do you remember it? The antiderivative of secant tangent is secant. All right, good. So what do we have here? Well, let's be careful. So we have the half. So I'm going to be careful here. 1/2. When you integrate secant tangent, that would be secant. Now, here's where we start being careful. A secant of what? Well, the insides are the same, so it's still the 1/4 x. You have to be careful. Because you have that 1/4 there, what do? Well, the answer, if you apply substitution, and you're very careful, but this is the kind of substitution that you should hopefully be able to do in your head, is you divide by 1/4, which really means you multiply by 4. So what we now have is that we really have 2 secant of 1/4 x. But wait a second, we forgot to write something down, the bounds. So from 0 to pi, 0 to pi. So we have 2 secant pi over 4 minus 2 secant of 0. Now, we're almost there. If we just knew what these values were. Do we know what the secant of pi over 4 is? Well, I hope. Now, maybe you're not quite so familiar with secant of pi over 4. How about cosine pi over 4? Do you know that? It's the square root of 2 over 2. Well, another way to say the square root of 2 over 2 is 1 divided by the square root of 2. Aha! So this is 1 over root 2, which is a very long, convoluted way of saying that secant of pi over 4 will turn out to be square root of 2. All right, how about secant of 0? It's not 0. What is it? Secant of 0, well, cosine of 0 is 1, so secant of 0, 1 over 1 is 1. So our final answer will give us 2 times the square root of 2 minus 2. And there we go. That is a fun problem. I like this problem. I like so many problems. You're probably like, Steve, why do you like all the problems? because I think they're beautiful. I really do. There's just, things work out so nicely. And so it's nice when things work out. You know, it's a sign that we're doing something right. And I like it when we're doing the right thing. All right, well, let's try some more problems. Our next problem. Find the volume of the shape formed by rotating the region where x goes from 0 to pi and y goes from 0 up to 2 sine of x, and we go around the x-axis. It even gives us a hint. I don't know if we need it, but it says 2 sine squared x is 1 minus cosine 2x. This is actually a really nice rule. This is called the power reduction, and it's one of the 6 trig identities you should know. So it's probably good for us to learn it at some point. I'm sure sooner or later we're really going to drill into it, but maybe not today. So let's think about our basic setup here. So we're going from 0 up to pi, so let's say this is pi. And now sine of x normally goes from 0 to pi in this way. 2 sine of x looks similar, it just actually just sort of goes up a little bit higher. So it goes all the way up to the value of 2. So there's our shape. This is the shape where x goes from 0 to pi and y goes from 0 up to 2 sine of x. So add a little bit of shading here. All right. Now, what's happening? Well, we're going to rotate around the x-axis. So we're spinning that way. So let's think about our basic thing. What's going on? Well, what's going on is we say, well, start with a small slice, and if you spin it, what shape gets formed? And the answer is you see a circle, or if you want to be fancy, a disc. And the reason we call it disc is there's a little bit of thickness here. It's not, there's a little tiny bit of thickness. All right, so what's the formula for the disc method? Well, we're going to add up, which means integrate, start to stop of little circles. So pi, a radius, squared, it's really our area, and then to make it a disc, add a thickness. So we have an area times a thickness, that's a volume. We're adding up our volumes, that's our total volume. Okay, so lots of these things are pretty easy to spot what they should be. So for example, our thickness. Well, our thickness reflects how we're choosing to slice things up. And in particular, we're thinking of moving x from 0 to pi. So here, our thickness will be our dx. Well, our bounds, we start at x equals 0, we end at x equals pi. All right? Now this pi is just pi, nothing changes, it's a constant. That leaves us with the radius. So our radius is this length. It's from the curve to where we spin. So this is our radius. Well, that's from 2 sine of x down to 0. So that would be 2 sine x. All right, well, let's see. What is that? Well, that's going to be the integral 0 to pi. Then we have the pi. If we square that, 4 sine squared of x dx. Now, how do you integrate sine squared of x? It's not one of our 10 basic things that we can take integrals of. So what we have to do is find a way to rewrite it. If only we had a hint that would help us know how we could rewrite sine squared of x. Well, we do, right? We know that 2 sine squared of x is 1 minus cosine 2x. We actually have 4 of them. So what we can do is we can really think of this 4 as 2 times 2, right? So we'll have a 2 sine squared of x and a 2 left over. The 2 and the pi, those are constants. So let's pull them out front. 2 pi, integral 0 to pi. Then the 2 sine squared of x will become 1 minus cosine 2x. And there we go. All right. Now, we're ready to integrate because we have pieces which are reasonable for us to integrate. So the integral, for example, of 1, well, that's going to be x. Notice we're integrating with respect to x, so that's our variable. How about the integral of cosine? Well, the integral of cosine is positive sine. We had a negative to begin with, so it's still negative. There's a 2x on the inside. What comes in the front? Anything? 2? A half? Something else? It's going to be a half. So you have to sort of say, look, if I have a constant multiple on the inside, I divide by that constant out in front. So because there's a 2x, divide by a half. If you're not sure, there's a way you can run it backwards. The way you run it backwards is say, let's take the derivative and see if I get what I started with. So if you take the derivative of sine of 2x, it would be cosine of 2x times 2. And so this half compensates for that times 2. Well, almost done, but we still have to evaluate 0 up to pi. Okay, so we plug in pi. So what do we have? We have 2 pi, then pi minus 1/2 sine of 2 pi. Plug in 0, 2 pi, 0 minus 1/2 sine of 0. I oftentimes don't write everything out, but you can. And whatever you do that helps you not make a mistake, do it. So what happens? Well, lots of things happen. The zeros go away. Sine of 0 is 0. How about sine of 2 pi? Sine of 2 pi is also 0. In fact, it almost all goes away except for that pi there. Times the 2 pi leaves us with 2 pi squared. And there we go. That's our answer. Beautiful. Nice. So simple at the end. Isn't it great when you get a nice, clean answer? There's something about a problem when the answer is relatively simple. It brings a smile to my face. I hope it brings a smile to yours too, and that you enjoy working on problems. That's how you get better at doing math, by the way, is you do problems. And the more that you do, the more you enjoy doing it. So let's keep enjoying it, right? So let's have the joy continue. Find the value a so that when the region from 0 up to sine x, or 0 to pi, x going from 0 to pi, is spun around the line y equals negative a, the resulting volume is 20 pi. Well, this is kind of a little different. What's different here? Well, what's different is we have the volume. The volume has been handed to us. It's like here is the volume. What we don't know is information about how we got the volume. So we know bits and pieces of it. So let's think about what we do know. And then once we know what we do know, we can figure out what we don't know. So we have our basic setup. Similar to a problem we just did, y goes from 0 to sine x, x goes from 0 to pi. So if here is pi, sine of x would do that. So our region that we're working over is this piece right up here. All right, so that's what we're spinning. But now we're spinning it around a different object. We're not spinning it around the x-axis. We're spinning it sort of off some offset line. So all the way down to here. So here we go. There's just some line down here, y equals negative a. And we're going to spin it that way. All right. And once we spin it that way, lo and behold, the volume that comes out will be 20 pi. All right. So we have an idea sort of in mind. And so the question is, what should A be to give us this right answer? All right, well, what do we do? Well, the answer, of course, is we think about the formula. So we know what the volume is. We know it's 20 pi. So we can say that 20 pi is equal to the volume, which the way we do this is, let's think about how we find this volume. So what's going to happen here this part down here is what happens when you spin it around. And you can see that we're going to take a small slice, and that as we spin, what do we end up forming? Well, we end up forming a shape that looks something like that. It's a washer. So we're going to use the washer method. So we're going to add up, whoops, let me change back to my more purpley color. We're going to add up from where we start to where we stop, pi. Then we're going to have our outer radius, and that's going to be squared. Subtract our inner radius, and that will also be squared. And then there's a thickness. So that's our setup. That's the formula. Okay, so let's go through and assign our little pieces here. A lot of these aren't so bad. We know the thickness. We can see that. We're taking slices here as we go. X goes from 0 to pi, so our thickness is our dx. Our start and stop, well, we're told what happens with x. We go from 0 to pi. So we're going from 0 up to pi. All right, so there's our start and stop. What about our radiuses? Well, we have to think about it. Now, the top, the further part, is the sine. So, if I'm going from sine of x down to negative a, that's the outer radius. So the outer radius is going to be, I'll be really careful here, we're going to take sine of x, subtract negative a, right? So it's high minus low. Sine of x, subtract negative a. And then the inner radius, well, the nice thing about the inner radius is it's actually pretty clean, because this is the line y equals 0. This is the line y equals negative a. The distance on the inside is always the same. So our inner radius is, you can think of it as 0 subtract negative a, or it just simply is a. All right, well, let's clean this up and see what we have. So we get that this is equal to pi integral 0 up to pi. If we square that, we're going to get sine squared of x, then plus 2a sine of x plus a squared. So that's sine squared, then 2a sine a, that's 2a sine x, excuse me, cross term, and a squared. All right, minus a squared. Okay, dx. And now we say, something nice happens here. The nice thing is the a squareds cancel. Woohoo! Which means it's actually going to be pretty simple to solve for a. Now, we do have a challenge. What do we do about the sine squared? Well, the answer is we're going to be very careful, and there's a nice rule. You can't integrate sine squared as sine squared, but what you can do is rewrite it into something more convenient. It's often a good tool when you're trying to solve problems involving integration. If you don't like the problem as written, rewrite it to something that you can. So sine squared, we can rewrite this as 1 minus cosine of 2x all over 2. So that's how we integrate the sine squared. All right, so keep moving forward. What do we have? Well, we have the following. Let's integrate piece by piece. So the integral of a half is a half x. The integral, and I'll be a little bit careful, there's a half, integral of cosine 2x, sine of 2x times another half. All right, that's okay. The integral of sine, well, all right, do you remember that one? Well, I don't think we've done the integral of sine yet. The integral of sine is negative cosine. Be careful, be careful. So it's one of these things about sine and cosine. It's always easy to lose track of which one is positive, which one's negative. So double check. Don't just rush. It's not about being the fastest. It's about being the rightest. I don't think rightest is an actual word, but we want to be correct. That's our goal. Okay, so let us now evaluate and see what happens. So when you plug in pi, well, what do you have? Well, you get a half times pi. So that's 1/2 pi. Then we have a sine of 2 pi. Well, sine of 2 pi is 0. Goes away. How about cosine of pi? Cosine of pi is -1. Think about the unit circle. So when we talk about the angles, we can really think about it in terms of the unit circle. So when we're talking about pi, that's going to be the point over here. And the cosine would be the x-coordinate. So that's why we say cosine of pi is -1. So -1 times -2a would make this a positive 2a, so plus 2a. Now, from that, we're going to subtract. We plug in 0. Half times 0, 0. 2 times 0 is 0, and sine of 0, 0. Cosine of 0 would be 1. So minus 2a. All right, so we're almost there. We're almost there. In fact, we're pretty close. So let's go ahead and now finish off. So what can we do? Well, there's a pi here and a pi there. So let's divide out to cancel. And if we do that, we come to the conclusion that what? Well, we have that 20 is equal to 1/2 pi and then plus 4a, because 2a plus 2a plus 4a. Now, we can move the 1/2 pi across. 20 minus 1/2 pi has to equal 4a, or divide by 4, a is equal to 5 minus pi over 8. And there we go. That's the answer. 5 minus pi 8. Well, I don't think we would have guessed that, but we don't have to guess. We work the problem, and the problem tells us what will happen. All right, good. Beautiful, beautiful. Okay, well, on to one more problem, right? At least one more. It's good to have more problems. So, our next problem. Find the volume when the region where x goes from 0 to pi and y goes from kind of a strange combination of curves to root x times sine x less than or equal to y less than or equal to x plus 2 sine x is spun around the y-axis. So this is actually the picture here. Sorry, I said y-axis, the x-axis. So that's our region. So our bottom curve, this is the curve y equals 2 square root x sine x. And the top curve, this is the curve y equals x plus 2 sine x. And our goal is say, hey, let's take this crazy looking shape, spin it around the x-axis, and let's see what we get. So I think the thing to do is sort of say, well, what setting are we in? So clearly we want to work with everything in terms of x. And so we should say, well, let's just take a small slice and we spin it. And what would we see? Well, what we'll see is a shape. This really is kind of a weird looking shape, isn't it? That when we spin it, we're going to see a washer, right? Yeah, that's very washer-like. So this is a volume of revolution, so it's a disk or a washer. It's a hole, so it's going to be a washer. All right, so now we say, well, let's start with our basic formula for washer. So we have our volume is equal to adding up pieces from where we start to where we stop. And what do our pieces look like? Well, it's the area of the slice, and the area of the slice is the difference of two circles. Outer radius, if you like the big radius, squared, minus the inner radius, or the smaller radius, squared. So big circle minus little circle, and of course there's the thickness. All right, so those are our pieces that we have to figure out. Now, let's dig into it a little bit. So our thickness, well, really, if you look at this, it's a very tiny, when we're going in the x direction, we're perturbing the x direction. So the thickness is a dx. Our outer radius, well, what would that be? Well, maybe let's hold off on that. Let's do our bounds. Let's celebrate the easy part, right? Where do we start and stop? Well, it told us 0 to pi. All right, good. Progress. It's always nice to have some progress. All right, now back here. Our outer radius. Well, we're spinning around the x-axis, so our outer radius is out to the further curve. So the outer radius is x plus 2 sine of x. The inner radius is, again, from the x-axis up to the inner curve. So that would be 2 root x sine x. Okay, now at this point, if you're not a little bit nervous about, like, these are not looking like great functions, then you haven't been paying attention with integration, because I'll tell you, integration gets really tricky really fast. But let's have faith that whoever wrote this problem wrote it because they wanted us to succeed. And I think we can succeed. I'm optimistic. So let us continue. So what do we have? Well, we now have the following. So this is equal to integral 0 up to pi. Now this pi is a constant. I can go ahead and pull it out in front. All right. So we have x plus 2 sine x quantity squared. So if we square that, that would be x squared. So square the first term. So think about it like a squared. Then you have the 2ab. That's the middle term. So 2 times x times 2 sine x would be a 4x sine x. Then you have to square the 2 sine of x. So that's plus 4 sine squared of x minus, and now you square it here, well, 2 squared would be 4, and x sine of x. Oh, somebody likes us. Somebody likes us. Well, of course, lots of people like you. You're a great person. But do you see what's happening? The part that's really hard, the part that we're probably least comfortable with at this point, maybe to the point of we're not sure how to do it yet, is this x sine of x. But notice what's happening. A plus 4x sine x, a minus 4x sine of x, when you put them together, it's sort of a matter-antimatter combination. They cancel each other out. Oh, life is good. Life is good. So, gone. Nice. The x squared, pretty straightforward to integrate that. The 4 sine squared, well, we've done that a couple of times actually in these problems. You're probably thinking, boy, we keep doing these same things over and over again. Maybe I should memorize what sine squared is. Maybe you should. So, in case you haven't memorized it yet, sine squared of x is the same as 1 minus cosine of 2x. All of that, of course, divided by 2. And then there's that multiplying by 4. So we can rewrite this. We have a pi out in front. Integral 0 to pi. Then there's an x squared. 4 times a half is 2, so plus 2 minus 2 cosine 2x. Now, each piece is not so bad. We can make progress. So, what do we have? Pi, integral of x squared, 1/3 x cubed. I'm going to keep a parenthesis here so I remember See, it's pi times the whole thing, not just pi times the first term. Plus the integral of 2, well, that's also not so bad, 2x. Okay, minus integral of 2 cosine 2x. Well, the integral of cosine is sine. Since there's a minus, it's still a minus. Now, let's think about what we put in front. There was a 2 to begin with. What are we going to end up with? Well, we can think of it as 2 halves, because we have to divide by that 2. 2 halves, also known as 1. So it'll just simply be sine of 2x. Evaluate from 0 to pi. Well, when you plug in 0, good news, sine of 0 is 0, 2 times 0 is 0, a third times 0 cubed is 0. So we got to plug in pi. So we end up with pi. We have 1/3 pi cubed, then plus 2 pi, and sine of 2 pi, and sine of 2 pi also goes by 0. So it goes away. So our final answer is 1/3 pi to the 4th plus 2 pi squared. Wow. A beautiful answer. Beautiful answer. And something that we can do. We have the technology. And of course, we're going to get even better technology because we're going to be able to learn more and more applications. All right. Well, good day. But keep working. Keep getting good at it. It comes with practice. Once you understand how to set things up, it becomes fun. And that's what we want. We want you to enjoy it. Have a good day.